section 2.5 is about continuity. Now, I've already used that word because the limits that it's easiest to evaluate are the limits that we can evaluate by simply plugging into the function. And those are limits of continuous functions. Our textbook is catching up with us now. They're ready to give us that definition as well. So let me repeat that. Definition. A function f of x is continuous at an x value a in its domain if. Okay. Now, I'm going to give you two versions of the definition. I like to start with the informal version and use that to remind me of what the formal definition is. The informal definition just says that what we get is exactly the same as what we expect. So I sometimes think of a continuous function as one where nothing weird happens. We always get what we expect. Now here we're talking about a function just being continuous at a particular x value a in its domain. So what we get would simply be the function value. That would be f evaluated at a. If I'm graphing, that would be where there's marker on the board or where there's ink on the page, where I actually have a point that's part of the graph. What I expect, that's going to be the limit as x approaches a of f of x. Okay. So what I've written in words here is my informal definition. What I've written in symbols here, that's the formal definition of what it means for a function to be continuous at an x value a. Now, I said at an x value a in its domain. Obviously, if a isn't in the domain, this left-hand side won't exist. Okay. Some books sometimes make a big deal about the fact that three things must be true. The left side must exist. Okay, a has to be in the domain. The right side must exist. We have to expect something, and they have to be equal. That's true. There are three parts to this equation. There's the left side, the equal side, and the right side. So in order for what we get to equal what we expect, we have to get something, we have to expect something, and they have to be the same. Okay, and so the beauty of continuous functions is because what we get is the same as what we expect. These are the ones where if we want to evaluate the limit, all we have to do is plug a into the function. Okay, so that's the definition of continuity if we're talking about continuity at an individual point. Often we'll just talk about functions that are continuous on their domains. So f of x is continuous on its domain if, and all we do is we take that definition for individual points and we require that it be true for every point that's in the domain. So if f of x is continuous at every x value in its domain. So that at every point in the domain, we get what we expect. The function value and the limit are the same. All right, so that's what continuity is. I want to just go over three common types of discontinuities. This isn't an exhaustive list. Functions can be discontinuous lots of different ways. I'm not going to attempt to record every weird thing that could happen. But here are three common types of discontinuities. Okay. So the first, I'm going to start by just illustrating it. Could be something like so, or could be something like so. Okay, Both of these are examples of what we call a removable discontinuity. The important thing here is that with both of these pictures, if I say the location of the hole is A, in both cases, the limit as x approaches A of f of x exists. Okay, so there is a finite number that I would expect to be the y value at A based on the nearby behavior. The difference is that it doesn't equal the function value. And there are two reasons that could happen. One could be that the function doesn't exist. The other could be that the function value does exist, but is a different number. Either of those, we classify the same way. We say that's a removable discontinuity. And it's removable because we could create a continuous function if all we did was redefine the function at one point, at that point A. Right now, A isn't in the domain, so f of A is undefined. If I say, well, let's just define it so that we fill in that hole, I've removed the discontinuity. Here, f of A is defined, but it's this y value that's a little bit higher up than I expect. If I were to redefine it, to move that y value down to fill in the hole, I removed the discontinuity. So if the limit exists, the weirdness is just what happens right at A. Either there's a hole and the function isn't defined at all, or there's a hole and the function is defined somewhere else, but I could remove that discontinuity if I just redefined the function to fill in the hole. Obviously, that would give me a different function, but that's a different situation from the other types of discontinuities we're going to see. So the second thing would be a jump discontinuity. Now, I'm going to just draw some pictures of a jump discontinuity. So I could have a function that looked like that. I could have a function that looked like that. Or I could have a function that looked like that. Okay. We're jumping in all cases. Now I can jump from a point to a hole. I can jump from a hole to a point. I can jump from a hole to a different hole. And for this picture, if there wanted to be a point somewhere else, that would be fine too. The significance here, if I make the location of all of these jumps be A, the significance here is that the limit as x approaches A from the left of f of x is different from the limit as x approaches A from the right of f of x, but both exist and are finite. So basically, I'm expecting a different numeric value coming in from the left or coming in from the right, so that the function jumps. Okay. Notice, this is not a removable discontinuity. Removable is when the limit, the two-sided limit, exists. And here, if the two one-sided limits are different, the two-sided limit does not exist. If I wanted to move the function, or change the function to create a continuous function, I'd need to either take this piece or this piece. I could move this piece down or move this piece up, but I can't just change a single point. If I just redefined the function at A so that I filled in this hole, I still have a jump. I'd need to move the point and drag the curve along with it. I'd need to create a continuous function, redefine the function at infinitely many points. It's a big difference from just being able to redefine it at one point. So if there's a jump discontinuity, both one-sided limits are finite, but they're different finite numbers. All right, and the third type of discontinuity that's very common is an infinite discontinuity. And as you might guess, that's going to be where we have a vertical asymptote. So I might see something like so. Maybe we're going up on both sides. I could have a situation where we're going down on both sides. And I could certainly have a situation where we're going up on one side and down on the other. I could draw a fourth picture where we're going down on the left and up on the right. Okay. If I have an infinite discontinuity, then I have at least one of the limit as x approaches a from the left of f of x, or the limit as x approaches a from the right of f of x, or the two-sided limit as x approaches a of f of x. At least one of these three limits is either infinity or negative infinity. In other words, I have a vertical asymptote. That's what it means to have a vertical asymptote, and we say that's an infinite discontinuity. Okay. So in this case, if I've got a situation like this, the limit exists as a symbol, but not as a finite number. So I probably should have said with removable discontinuities, the limit exists and is finite if it's a removable discontinuity. So there's sort of this question of, does infinity exist? Well, it's a concept, it's a symbol, one could make all sorts of arguments, but for the purposes of defining our discontinuities, a removable discontinuity is one where the limit exists as a finite number. So here, for the purposes of describing our discontinuities, something like this where I would say the limit is infinity, that doesn't count as the limit existing for me to classify this as a removable discontinuity. This would be classified as an infinite discontinuity.